the book says something that's just the opposite. And I've talked to Dr. Ling and other colleagues about this. So in the book, I wrote some notes here in my notes. In the 7th edition, and you can read this for yourself, in the 7th edition, so that's the edition that I'm using, the book says that the presence of food in the stomach that elevates the hydrochloric acid secretion. You know this from physiology, that when we eat, that the hydrochloric acid secretion by the stomach is increased, right? Mm-hmm. So what would increase in hydrochloric acid secretion? What effect would that have on pH? It would lower it. It would lower. Okay, so now here I am telling you that food dilutes. That's why I'm saying there's some controversy. I'm saying that food dilutes this and causes an increase in pH. And page 491 of your, not 491, 391 of your textbook, it says, without explanation, it says, well, it does give an explanation. It says that secretion of hydrochloric acid that occurs when we eat causes the pH of the gastric contents to go down. In other words, even though we got this dilution effect going on, it's like the secretion of the hydrochloric acid is going to trump the dilution effect. In other words, we got two things going on. We got the dilution effect going on from food, but we also have food causing the secretion of hydrochloric acid. Secretion of hydrochloric acid tends to pull the pH down. The food tends to increase the pH because of the dilution effect, okay? So I don't know definitively which one is going to happen, where it's going to be, or if it's going to be the same way each time. I haven't done the research, but what I suspect is that when we first start eating, or even before that food reaches our stomach, your mouth starts watering and the digestive system kicks in. So maybe at the beginning of a meal, maybe the pH will go lower because of the secretion of hydrochloric acid, and it's not that much food in the stomach yet, so maybe you're going to get a lower pH early on, but as I eat more and more food, the dilution effect might take over. Now that's just me hypothesizing. I don't know that for a fact. But I am telling you that the book says that food will cause a decrease. On page 391, you can read that food causes a decrease. Other sources say that because of the dilution of the food, that there is an increase in pH. Can you visualize, or do you see those two processes as possibilities at least? Okay. Yes. Very good.
But which process are we going with?
Okay, like I said, I don't have a definitive answer. I mean, both of them are possibilities. I think, like I said, that maybe early on, okay, maybe the acid secretion overrides today because you don't have that much food in the stomach at the beginning of the meal, but perhaps as you continue to eat more and more food, that the dilution effect takes over. So that's the way I'm trying to reconcile. Right now, I want you to understand that, both of those processes are possibilities. In other words, a decrease in pH as a function of food, and also the possible increase as a result of the so-called dilution effect. That's, food does affect the pH, and it can affect it in either, it can go up or it can go down. Okay, I have my notes, but you already know acidic drugs will dissolve more readily in the intestines, in the small intestine. And we've already said that the basic drugs will dissolve more readily in the stomach. Gastric emptying and GI motility. So that's all I want to say about pH. The next physiological factor I want to talk about a little bit. And let me tell you this, it might not affect you guys because hopefully you'll be gone. But at some point in time, in the college, it was my suggestion, and I might be gone too. Okay? But, I came up with this concept of knowledge on demand that we should have of our students. Okay? I'm just kidding. So there are certain things that you learn in your classes that you should not have to go back to study and review. in my opinion, pH is one of those things for a pharmacy student. So for instance, you know, you're in pharmacokinetics, and you know, one of the problems or the question on your exam asks you to calculate. I think I did this on exam 1 or exam 2. I gave you a hydrogen ion concentration and asked you to calculate the pH, or I gave you the pH and asked you to calculate the hydrogen ion concentration. There are certain things that as pharmacists, students, and practitioners, when I say knowledge on demand, that means that you know that if and you have, if it works out right, you will have this list of things too. So it ain't gonna be something that's secret that the instructors just have, but you will have this too. So you're in a therapeutic course, and they didn't even lecture on pH, but now one of the questions on the exam actually calculate pH. You gotta be able to do that without, you know, without saying, well, hey, you know, you didn't cover pH in your lectures. There are just certain things that we should know. Percentage strength, you know, all of those different representations of the strength of a solution, percentage strength, ratio strength, parts per million, parts per billion. That should be just like that. You shouldn't have to go back and study it. Okay, so I'm just sharing that with you. So I kind of feel that way about GIPH. Another physiological factor is gastric emptying. Gastric emptying, and I'm gonna group these together, and GI motility. Gastric emptying and GI motility. Now, when we talk about gastric emptying, and this is oversimplified, you know, that food has to, you know, go, you know, down the esophagus and it hits the stomach first. I mean, the mouth is part of the GI tract also, okay? And the saliva, you know, starts the, you know, just the mastication of the food, chewing, and the saliva mixing with saliva starts the digestive process. But the major parts of it is going to start, you know, once the food hits the stomach. Gastric emptying pertains to the emptying of the stomach contents. Okay, so that food that we eat, or those liquids that we ingest, they're only going to stay in the stomach for a certain amount of time, then they're going to move on into the small intestine. So gastric emptying has to do with emptying the GI fluid from the stomach to the small intestine. That's my simple explanation of it. Okay. The GI motility component is once it's in the small intestine, you know that things move along the small intestine, you know, because of peristalsis or whatever the case may be. So it's in the, you know, the duodenum and the jejunum and all those fancy parts of the small intestine. And it's moving, it's not just static in the small intestine. So it's drug or food even is moving through the small intestine. That's where the GI motility comes in. So gastric emptying from the stomach to the small intestine. GI motility, well, it's in the small intestine, but it's moving, it's mobile, okay, as it moves along the small intestine. Okay, so I just want to make a quick distinction between those two processes. Factors that promote gastric emptying. Now you have an idea of what gastric emptying is. That's from the stomach to the small intestine. Factors that enhance or promote gastric emptying tends to increase the absorption rate of the drug. Okay. Think about that. If I can get that, if I can get that drug, the faster I can get that drug from the stomach to the small intestine, where we say that most absorption is going to occur in the small intestine, wouldn't that increasing gastric emptying tend to increase the rate of absorption? Because a whole lot of absorption is not occurring in the stomach. So the faster I can get it to the absorption site, the major absorption site, i.e. the small intestine, that's going to speed up the overall absorption process. Does that make sense? You know, if I take a drug and it's just sitting there in the stomach, it might take forever to get absorbed from the stomach. Okay? So factors that increase the gastric emptying tend to increase the absorption rate of the drug. And again, that's because, you know, the large surface area in the small intestine. On the other hand, factors that decrease gastric emptying, in other words, they slow down gastric emptying, tend to slow down the absorption rate, because now that drug is not going to be able to get to the small intestine as quickly. Small intestine is where it's happening, okay? So the drug is just lingering in the stomach, then that's going to tend to slow down the overall absorption rate of the drug. I've already mentioned penicillin, not penicillin, but erythromycin but also drugs like penicillin G, Pen G, they undergo acid instability. So if a drug like penicillin G, some of the other penicillins, if I take that drug orally and it's just sitting there in that acidic environment of the stomach, okay, it's unstable. You probably know that from medicinal chemistry or other courses. So if that penicillin just sitting there in the stomach, okay, that's going to interfere with the absorption process because the drug itself is going to be broken down. It's unstable in those acid conditions of the stomach. Okay? I have in my notes here that gastric emptying is retarded or slowed down by fats and fatty acids in the diet and food in general. I'll repeat that. That gastric emptying is retarded or slowed down or inhibited by fats, I'm talking about dietary fats, fatty acids, and just food in general. Just solid food in general tends to slow down gastric emptying. Okay. On the other hand, gastric emptying is increased by fluids. So when we ingest fluids, that tends to speed up the movement of those fluids and those contents in the GI tract to the small intestine. Gastric emptying is increased by fluids. Some of the drugs, some examples of drugs that slow down gastric emptying, you can write these down. Atropine slows down gastric emptying. Propanthyline slows down gastric emptying. Amitriptyline. What class of drug is amitriptyline? You all studied that? Antidepressant. Okay. Imipramine slows down gastric emptying. Desipramine. What's the relationship between imipramine and desipramine? Chemically speaking. Yeah, desipramine is actually what, an active metabolite of imipramine? Okay, very good. And then chlorpromazine. So I repeat those examples. These are just examples. I'm sure there's a whole bunch more in your textbook. Okay, I'm holding you responsible for these. Atropine, propanthyline. What effect? What pharmacological effect of atropine will cause the slowing of gastric emptying? Huh? Is it anticholinergic? I'm asking. Is cholinergic or anticholinergic or something like that? Okay. That's the kind of stuff that I'm saying that for, even though you can tell I'm weak in pharmacology, but that kind of stuff should be knowledge on demand. That hey, you know that hey, it's due to, is it cholinergic or anticholinergic? Okay, that's slowing down, you know, and it's probably going to have the same effect on GI motility when we talk a little bit about GI motility. So I'll repeat those drugs. So gastric emptying is retarded by atropine, propanthyline. What about the pharmacological effect of propanthyline? Propanthyline. That will cause it to slow down gastric emptying. Is that anticholinergic also? Amitriptyline, imipramine, desipramine, and chlorpromazine. Okay, so these are all examples of drugs that will retard or inhibit or slow down gastric emptying. Okay? Gastric emptying is promoted by hunger. So hunger will increase gastric emptying. You know, when we're hungry, our stomach is growling and all that kind of stuff. Okay. That causes an increase in gastric emptying. Anxiety, when we're stressed out, you know, that causes an increase in gastric emptying. And I have one drug as an example, metoclopramide. Metoclopramide will increase I think I'm spelling it right. Metoclopramide. Let me check my notes, see if I'm spelling that right. Yeah, that's it. Okay. So hunger, anxiety, there are a host of drugs I'm sure that would increase gastric emptying. What effect, multiple choice question now, connect the dots. What effect would a dose of metoclopramide have on the absorption rate of a co-administered drug?
It would increase it.
It should increase it. That's what that's the kind of connection I want you to make. We've already said that things that slow down gastric emptying retard absorption. Things that speed up gastric emptying, they're gonna get those drugs to the small intestine faster. So yeah, I would predict that metoclopramide would speed up the absorption rate of co-administered drugs because it's gonna cause those co-administered drugs to get to the site of absorption, i.e. the small intestine faster. Very good, okay. And then I have here that the gastric emptying time, ranges anywhere from 30 minutes to 4 hours, depending on, the food and emotional state and all these other factors that come into play. 30 minutes to 4 hours. In other words, when I ingest a drug or food or whatever into my stomach, it can stay in the stomach anywhere from 30 minutes to 4 hours before it even sees the small intestine. So that's a pretty wide range, okay? Oh, I have another interesting piece of information in my notes here, and that is that our posture can affect gastric emptying. Okay, so for instance, if we are lying down on our right side, like when we're in bed or something like that, and we're lying on the right side, that promotes gastric emptying. And I guess it has to do with the way the stomach is oriented in the body. So lying on the right side promotes gastric emptying. On the other hand, if we're lying on our left side, that retards gastric emptying. Now, in general, that's probably not maybe such a big concern, but it could be for an institutionalized or hospitalized patient, okay, to know that. Okay. So posture can affect gastric emptying, and another thing I have in my notes is that gastric emptying may be, remember the other day when we were talking about, I think, physical chemical factors, we talked about rate limiting step. The gastric emptying could be the rate limiting step in the absorption process, and that's true for acetaminophen solution as an example, where gastric emptying is the rate limiting step. Now I'll try to diagram what I mean by that quickly and not spend a whole bunch of time on it. Okay. So we have the drug product. So I'm gonna write the steps a little bit differently than I did the other day to make this point about gastric emptying could be the rate limiting step. So that drug product, okay, and that drug product that we take, we're gonna assume that it's orally. It's gonna have to be drug in solution. So I'm skipping the dissolution process. We know that it's a solid drug. You got to break down before it goes into solution. So drug in solution in the GI tract. In GI tract. And then we just say drug, we got the absorption process. Absorption. That's absorption process, this process here. And then we're gonna have drug in the blood. Drug in the blood. So on Friday or even early next week, we'll talk more about, we'll develop a model for drug absorption. The folks in the lab yesterday, they're already experts at using at least one of the major equations that pertain to drug absorption. And after today's lab, and the Wednesday's lab will be experts too, so we just did like some pre-calculations. Okay, so what I was saying was that if gastric emptying, I should have put another step here. Drug in stomach. Let me put one more step here. Drug in. Let me put the gastric emptying step. So let's make this step, and I apologize for messing up your notes if you're taking notes. Let's make this step here GI emptying step. Okay. GI emptying. So this is in the drug in solution, let's say in the stomach. so I can, better illustrate what I'm trying to do. Drug and stomach. And then I have the GI emptying step. And then I have drug. Where am I gonna put drug where after GI empty? In the small intestine, exactly right. That's right. Okay. So I want drug in small intestine. And then the absorption step is here. Okay. So what I was saying is that absorption. So now we got drug in the blood. Drug in the blood. So after it's in the intestine, then it's absorbed and it goes into the bloodstream. So if this GI emptying, remember we talked about rate limiting step. If this is the rate limiting step, that means that this is the slowest step in the process. Okay. Then we're going to learn how to measure the absorption rate and the absorption half-life or whatever the case may be. But if this is the rate limiting step, we can do all that fancy pharmacokinetics, we want to, okay? This step right here would be actually, if it's the rate limiting step, will be actually governing the absorption of the drug, okay? Now in most instances, this is the rate limiting step, okay? But if this is the rate limiting step, moving from the stomach to the small intestine, if that's a slow step, it don't make any difference. For instance, if I want to change the dosage form from a tablet to a solution. Now usually you would think that a solution is going to be absorbed more quickly because the drug is already dissolved. But if this is the rate limiting step, you can change that dose from a tablet to a solution if you want to. It ain't going to speed up the absorption process because here's the slow step, not this one right here. So that's the point I'm trying to make. If gastric emptying is actually the slowest step in the process, okay, then when we get into more detail with absorption, then what we're calling the Ka, the first order absorption rate constant, and we're measuring the absorption half-life and all that kind of stuff, we would actually be looking at this step. The folks with the alphabets behind their name, they say, well, hey, the half-life of absorption, they just assume it's associated with the drug product, but it might not be associated with the drug product. It could be associated more with this physiological process, gastric emptying. That's the point I want to make there. And an example, I said this a few minutes ago, acetaminophen that's administered as a solution. Okay. When acetaminophen is administered as a solution, okay, here's the rate limiting step here for that acetaminophen solution. Not this one. So when we look at the pharmacokinetics of acetaminophen, some laugh, I'm very sensitive. And I have 2 more sessions to complete, okay, so don't be laughing at me. I'm just teasing y'all in my own shit. You might break up. No, I'm just teasing. Okay, so acetaminophen in solution is an example where GI emptying is the rate limiting step. Okay? So when we look at the pharmacokinetics of acetaminophen solution, as it goes into the bloodstream, we're not really measuring this step right here at all. We're looking at the rate that's determined by this step. The mean transit time for GI motility. So I don't know the technical definition of transit time, but for us, let's say the drug is in the intestine now. Okay. So it has a time, it has a certain amount of time that it's going to take to get, through the small intestine. Okay. That time, that average time, which I'm referring to as the mean transit time in humans, is about 4 hours. That it can vary greatly. It can vary greatly. The time that it takes for the drug to pass through the small intestines is approximately 4 hours. Okay. Approximately 4 hours, but that can have a wide variation. Just like we said, gastric emptying anywhere from 30 minutes to 4 hours. I think I saw some values in your textbook that went all the way up to like 12 or 13 hours for transit time. So that 4 hours is just an average time that you know, drugs and food and stuff would take to go through the small intestine, so-called mean transit time. Metoclopramide also, it will increase GI motility, just like it increased gastric emptying. Metoclopramide, the same drug right here. It increases GI motility. What effect would you predict metoclopramide? Let's say the drug is, we have a drug that we're taking, and then after that drug is administered, we administer, let's say 2 hours later, we administer a dose of metoclopramide. What effect would that have on absorption? Perhaps, I'm just guessing, I don't know. The metoclopramide speeds up GI motility. It's a good chance, and you know, optimal absorption, very good. Optimal absorption is going to occur in different portions of the small intestine. You know, you got the duodenum, the jejunum, and the ileum or whatever. But if I give a drug such as metoclopramide, and that previously administered drug is in that window in the small intestine for absorption, and I speed things up, that might rush the drug on through the small intestine, and it might not be optimally absorbed because it's speeding up the transit of drug through the small intestines. Metoclopramide is. So if I co-administer metoclopramide with another drug, okay, it's a chance. I'm just, you know, that other drug could be rushed through the small intestine, and then the absorption might not be as complete as it may have been without metoclopramide. So this ain't a rule or anything like that. I'm trying to get you to think of some possibilities. Okay. All right. So what if situations? And I'm going to stop right there. The only other thing I want to cover, that's all I have to talk about before is gastric emptying. I want to talk about, and I'll do this on Friday, we'll be through it with this, and we might be able to start on the absorption model on Friday also. I hate to do two major subjects in the same day. So normally, when we finish this up on Friday, I'll be through, but we're a little bit behind, and I want to make sure we have something to do for next week in laboratory. So maybe I can start on the absorption model after we finish this up and make an assignment for you next week in laboratory. On Tuesday next week in lab, even though I'll probably assign you some problems on Friday if we start on the absorption model, I'm probably definitely going to have to lecture a little bit in lab on Tuesday of next week, so you'll have enough information to, you know, to complete the rest of the assignment. So on Friday, I want to talk about the effect of foods on drug absorption. We've already talked a little bit about what food does and malabsorption. So effect of food, that'd be the sixth subtopic, effect of food. So I'll talk about that. So we cover bang, 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 bang. And the last one, these are short, so it shouldn't take me no more than about 15 minutes or so to cover these two. Malabsorption. So, you know, some drugs and some diseases can cause us not to be able to absorb food and drugs efficiently. So I'll talk a little bit about malabsorption. And then we'll be through with physiological factors. I think after that, we'll just cover we'll just go right to the pharmacokinetic model for absorption. Any questions? Question? Yes, ma'am.
What chapter are you on in the book?
It's in your, was it 14?
14.
14. It's in your lecture schedule.